Okay. Okay, now we have 15 students with us now. Should be another half. Okay, our Korean students here?
Yes.
Okay, yeah, because you thought that this week is a public holiday, eh? So actually, yeah, Malaysia has the highest number of public holiday in the world. That's why I'll give you our Malaysian calendar, because some public holidays are just for a few states, and sometimes it's for the whole country. Eh? Okay. Okay, I think we can start now. Okay, actually, I've already checked the room given for this class. A new building. Actually, it's a studio room. It's a studio room for 20 students. Currently, because of the distance that we have to keep, it is only allowed for 20 students. So I hope that you all don't mind if I carry out this course only online, but for the final presentation, I might be able to divide you into two groups. So there will be like 18 students at each session, so that we can use the room. Is it okay? Or you still want to have a physical class? Is it okay, students, to have online class?
Okay.
Because actually the room AST1 is only for 20 students. Okay, so we have 35 number of students, so it would be enough. So only for the final presentation we can meet each other. And also I hope that all of you, the groups that have divided you into, group you into 10 groups, so you can have discussion, physical discussion. So you can just keep your distance because there are only 3 or 4 of you. Okay, so I'm going to share my slide for today. So next week, okay. Before that, next week is online presentation, very short presentation for each group. Actually, should be you should present. We have 120 minutes plus 60 minutes, so we have 180 minutes. So actually each group can have 10 minutes for presentation and 8 minutes for question and answers. Okay, so I hope that all of you have started, you know your group members, so you have already started finding the source and location of the water that you want to treat in your treatment plan. So I hope that next week the presentation will be basically on the source and location of the water from the reference that you get, or you can not only from the journals. You may also contact any agencies or whatever body that do study for a water source. You can also get the or also from websites. From websites, any source that is giving you the correct analysis of the quality for the water source. So the first one is about the source and location of the water that you want to treat. The second one is about the water quality analysis. They must be able to present the table on the water quality. So I want to see, as I mentioned before, that I need all of you to treat at least 3 parameters listed in the table that I've shared during our second week of lecture. Water quality analysis, and then you need to compare with the present guideline, just to highlight the one that are not meeting the that do not comply with the guideline that we have. And I want to show whether I want you to show what are these 3 parameters. And you can also have more than that. You can have at least minimum 3. And then you also need to present the water quantity estimation that you want your treatment plan to be built. Okay, so you have 3 things that you need to address. First, the source and location of the water source. Second one, the water quality analysis compared to the present guideline. And the third one is the water quantity estimation for your water treatment plant. Okay, I'll share with you our slide today. So today is, okay, can you all see my slide? Can you all see the slide just now?
Yes.
Okay. Okay, water treatment, coagulation and flocculation. Okay, we have already had one lecture on filtration unit, central filtration unit. So for that one, since at that time we are still not comfortable with the number of students in the class. We still have some students coming in, so I don't give you any homework. Actually, I don't give you any homework or quiz for filtration unit. But what I want to do to make sure that you understand, I give you one assignment. I want assignment for you to copy with your handwriting to copy all the examples that I give, the calculation of the examples. And also you have, because in the example, some of the calculation, I just put the values, but I want you to handwrite the example once again so that you will understand each of the calculation. And I want you to provide all the units in the when you do the calculation and also in the answers. So make sure that you understand all the calculation, because if we do bit by bit, you understand all the section, you won't have problem with your final exam later. You understand all the materials from the slide and also from the maybe quiz or homework, then you don't have any problem to answer for your final examination. Okay, so for this week, this is about water treatment, coagulation and flocculation. As I mentioned before, that I don't actually follow the treatment terrain because some of the units you may get this unit earlier or some later. So I don't want to fix for you. So I started the lecture with filtration unit, and then followed by this week is on the coagulation and flocculation. Okay, so this is the diagram of a typical treatment facility where you have your raw water coming in, you can have your coagulation and also the flocculation unit. Sometimes they are combined, sometimes they are separate, sometimes the flocculation is also together with the sedimentation process. So here 3 is the settling, 4 is filtration, and chlorination, the disinfection, clear well storage, and the pumping to distribution system. So this is just a typical treatment facility, but of course depending on your water quality characteristic, you can arrange the unit operations that the water need to be treated. Okay, so today is on the coagulation and flocculation. Okay, so actually coagulation, coagulation and flocculation, actually it is 2 consecutive process. Usually occur with coagulation first and then followed by flocculation. Actually, these processes are used to remove colloidal particles from water. So colloids are very small particles. They are very small particles because these colloids, they can cause turbidity and color, color causing and turbidity due to these colloids. And also they are very small, can be 0.1 micron. 1 micron is 1 times 10 to the minus 9, 1 times 10 to the minus 6 meter. So this is 1 micron until 10 to the minus 9 meter. 1 micron is 10 to the minus 6. So this is the colloids range. The classification based on the size. So this is the colloids that we want to treat. So they are very small particles. They cannot be removed by sedimentation because sedimentation is by gravity, but colloids they are very lightweight. They are very lightweight, so they cannot be removed by sedimentation, and also they cannot be removed by filtration. Because they are very small. They are very small. Okay, sorry. Okay, So what are the examples of colloids? They can be soil particles. Okay, so, sorry, my handphone. Okay, they can be due to they can be soil particles, bacteria, viruses, and color-causing materials. Yeah. Okay. So why they cannot be removed? Because they are very stable in solution. Because these colloids, they are very stable, and theoretically, they will stay there forever. If we have colloids, they will stay forever in our tank unless an action to destabilize them is done. So coagulation and flocculation are the two processes used for this destabilization. We need to destabilize. Okay. Actually, colloids, most of them are naturally occurring particles in water, and they are negatively charged. Most of them are negatively charged. Because they are negatively charged, they repel. They are lightweight. They cannot be settled using sedimentation process. They are negatively charged, so they repel. And these small particles of colloid will remain suspended almost indefinitely if you don't do anything in your water treatment. Okay, so this is, you see the turbidity flow chart from surface water, one of the example, because coagulation, flocculation is almost a must for surface water, but for groundwater, sometimes you need this coagulation, flocculation, but sometimes are not. But for surface water, this is almost a must you need for your water treatment. So turbidity can be caused by suspended solids and also the colloidal particles. So these colloidal particles, they are light electrically charged particles, negatively charged particles to be more exact. So, but for suspended solids, they can be settleable or non-settleable. Settleable, they are heavy particles. Non-settleables, uncharged light particles. So they will not be affected by coagulation. Also, flocculation, they will not be affected, but by sedimentation and filtration, they will be removed. For sedimentation, around 60%. For filtration, around 35%. But for colloidal particles, they are light, negatively charged particles. So for coagulation, coagulation will convert these particles to uncharged light particles because they destabilize the particles. And flocculation will convert the particles to heavy particles to form floc, so that they can be removed using sedimentation and filtration unit. Okay, so this is why we need the coagulation and flocculation process. Okay. Okay. So as I mentioned just now, this actually the colloids, they are negatively charged. They are negatively charged. So this is the colloids, the negatively charged particle. It is surrounded by a fixed layer of positive ions here. Positive ions, they surrounded any attracted to the negatively charged colloids by electrostatic attraction. So this positively charged ion is attracted to the negatively charged ions due to electrostatic attraction. So and we call this is a stern layer, or fixed layer. This is the stern layer, and this is the stern layer which is fixed, because this electrostatic attraction is very strong here. Okay, so then this layer, it is surrounded by movable diffuse layer here of counter ions, the positive ion, but with lower concentration, but with lower concentration than in the fixed layer here. Okay, okay. So these two layers, we call this double layer theory. Double layer theory. This is the fixed layer, and this is more movable diffuse layer, and this is what we call double layer theory. The surface between the layer is called the shear surface. And the surface between these two layers, we call this shear surface. Okay, so the positive charge attached to the colloid in the stern layer, actually they are not enough to neutralize the negative charge of the colloid. So there is net electrical potential around the colloid. So we have this negative and then this positive. Then the electrical potential, the electrical potential at the shear surface here, we call zeta potential, measure of the repulsive force of the colloid to other colloids having the same charge. So this is colloid. We have another colloids. So the measure of the repulsive force of the colloid to other colloids having the same charge, we call zeta potential. The measurement of the force, we call this zeta potential. Okay. So we have these two. The electrostatic repulsion for a stable colloid, the net energy is repulsive. So these negative colloids repel other negatively charged colloid with respect to the dimension, dimension of the distance, the distance here. Okay, so this is the force is linearly measured to 1 over d squared, the electrostatic repulsion force. And then we have another force, intermolecular attraction, or the van der Waals force. So the van der Waals force, this is okay. The van der Waals force is 1 over d6. D is the distance, distance between the two negatively charged colloids. So this we have a lower force which is called van der Waals force. Okay, between the two colloids. Okay, the colloidal destabilization and agglomeration. So it was illustrated here, the previous slides, that colloids are stable because of the net repulsive force between them, and consequently they will stay stable in suspension unless this net repulsive force is neutralized. So you neutralize the negatively charged force. So the process of neutralization, neutralization of the repulsive force is called destabilization. And destabilization is achieved by a process called coagulation. Okay, so coagulation is the process of destabilization of colloids by adding chemicals or coagulants. You add chemicals or coagulant to destabilize the repulsive force, and with a counter charge. So actually the coagulants are positively charged. The counter charge to the negatively charged particles are to neutralize the charge carried by the colloids. So this will reduce the repelling force and gives the opportunity for the attractive forces to prevail and allow the particles and make them ready to agglomerate for the flocculation process and form bigger particles. So the second one is the agglomeration or the flocculation. Yeah. So after destabilization or coagulations, particles will be ready to track and agglomerate and form flocks. But this agglomeration is slow. So they need help to accelerate the agglomeration. So what do they do? So this perhaps we call this flocculation. So what we do during flocculation is we provide slow stirring or gentle agitation to agitate the destabilized particles just now due to coagulation and form a rapid settling flock. So this one sometimes, gentle mixing increases collisions between the particles. Rapid mixing destroys the flock. So during flocculation, we have to provide very gentle mixing. Okay. Sometimes if it is not, it is very, very slow, then we also need to another types of chemicals during the flocculation process. Okay. So coagulants are chemicals that are added to water to destabilize colloids. So the most common coagulants given in the table here: aluminium sulfate, sodium aluminate, polyaluminum chloride, ferric sulfate, ferric chloride, and ferrous sulfate. Okay, so these are the coagulants. Okay. Okay, this the most common coagulant that we use is alum. So alum, this is the commercial grade alum that we can buy with a molecular weight of 594. So density is from 600 to 11,000 kilogram per cubic meter. So this is the commercial grade. This is the reagent grade. The color can be tan to grey, green in color. So the aluminium sulfate, they can be present. You can get the aluminium sulfate in dry or liquid form. So dry form is most common. Granular is the most widely used. You can also have the type, the powdered type, and also you can have the lump form. So the dry chemical may be shipped in bags or in barrel. Okay, so this is aluminum sulfate. The second most common coagulant being used is alum. Alum is dissolved in water. No, this is alum. This is alum actually. Alum is dissolved in water at concentration of 3 to 7%. 5% most common. Then fed to the raw water by chemical feeders, the dosage pumps. So in the coagulation unit, we need to provide the dosage pump. So reason of diluting coagulant before injection into raw water is large volumes are easier and quicker to disperse into a large body of raw water than smaller ones. So usually the most common one, you use the dry alum, aluminum sulfate, and then you dilute. You dilute so that it's easier and quicker to disperse. And also sometimes if you are not that accurate in the in dispersing the alum sulfate, if you have a very diluted one, then it's not going to give you a big mistake in overspending on the amount of the alum. And the optimum range used is 6 to 8. Aluminum hydroxide is relatively insoluble within this range. So what we want to do is we want to just destabilize the colloids, but we want to collect back the aluminum hydroxide. We don't want the aluminum hydroxide to be in your water. That's why pH is very important, because we want to make sure the aluminum hydroxide is insoluble. Insoluble, because if the pH is very high, higher than 8, you will get soluble aluminum hydroxide also. It's aluminum hydroxide, but it's soluble. So it will be in your drinking water. And the pH is very low. You also get soluble aluminum hydroxide. So in practice, most water treatment plants utilizing alum operate at pH 6 to 7.5, and with alum dosage of 5 to 50 milligram per liter, because in the range of insolubility. Okay, by having this pH and also the dosage of this dosage, you will get aluminum hydroxide that is insoluble. So the exact dosage must be determined for each water batch using a jar test. That's why if you go and visit a treatment plant, the influent to the water treatment plant, there will be a pipe going into the lab, because they need to do experiment, the jar test experiment to determine the exact amount of alum that is needed for that batch of water. Okay. Okay. So the coagulation chemistry, you can see aluminum sulfate and water, you will get aluminum ion and then sulfate, and then water again. So the aluminum ion will react with the colloids so that the surface charge is neutralized. So this is the optimum pH. Okay, since the coagulation reaction results in the decrease of the pH, it is a common practice to add lime. Okay, so usually they have this aluminum sulfate and you have lime together with the coagulant to increase the pH, consequently countering the effect of pH decrease. Of course, you know that pH decrease is something that you don't want because some chemical reactions occur during that very low pH. So we don't want any chemical reactions to occur for your drinking water that have been treated using the coagulation flocculation process. Okay. Okay. Sometimes this is the second most common coagulant used is iron salts. So this is the ferric sulfate, can be ferric chloride, can be ferrous sulfate. They are less expensive than alum but can cause color problem if the precipitate is not removed completely. So there are pros and cons in using these iron salts. Okay. Okay, this ferric sulfate, the molecular weight is 399.9 gram per mole, available in dry form as granules, most common, or as powder. So the optimum pH is 3.5 to 7 and above 9. Ferric hydroxide is relatively insoluble within this range. So the typical dosage is 10 to 250 milligram per liter. So this is the reaction between the sulfate with natural bicarbonate alkalinity. So because if the natural alkalinity is insufficient for the reaction, then you have to add lime. Just now we have I've mentioned that pH is very important, and this ferric sulfate or alum they are taking up alkalinity. So you have to make sure that if alkalinity is not enough, the pH become very low, then you have to add lime in the coagulation process. Okay. Okay. You can see that using aluminum sulfate, finally you will get sludge with aluminum hydroxide. So aluminum ion actually compounds can give bad impact to your health. It can cause Alzheimer, the disease called Alzheimer. And usually, actually, even though we in Malaysia, we don't throw this. We don't bring this aluminum hydroxide sludge from the water treatment plant to Quality Alam because the charge is quite high. I think about 1 ton is about 2,000 ringgit. So we don't bring this sludge to Quality Alam, but we know that it is harmful because we don't want to increase the water supply rate to the consumers. So, but therefore, it is very urgent need. It is an urgent need that you use natural coagulants in your water treatment plant, especially wastewater or water treatment plant. You can use natural coagulants. So there are many studies. There are many studies being done that you use natural coagulants. The most common one is moringa seed. In Malaysia, we call this apa ni, kacang kaloi, moringa seed. Moringa seed you can use as coagulant. People also started using many things for these natural coagulants to replace the chemical coagulants. Not only due to economic reason, but also due to health reason. Okay, so in your water treatment plant design, what I want to do, if you use this coagulation flocculation process, I want you to use chemical coagulant because it is the common one that you people are using in water treatment plant. But at the same time, I want you to include one natural coagulant. I want you to prepare how you prepare these natural coagulants to replace the chemical coagulants that you use, and I want you to calculate for your since I've already given 3 or 4 members in a group, so I want to have more on your design project. So you use chemical coagulants if you need to use coagulation and flocculation process, and at the same time I want you to provide a section on this use of natural coagulants. Okay, so you need to find a reference or literature or research that use natural coagulants. So maybe in Malaysia, the natural coagulants usually, because usually if you want to use natural coagulants, one of the factor that we take into consideration is the whether we can find these natural coagulants easily. So for each group, since we have Indonesian and also Korean members, I want to get at least one coagulant that you can find not only from Malaysia but also from Indonesia and also from Korea. Natural coagulants that you can use to replace the chemical coagulants. So using these natural coagulants, I want you to show of course, the photo of the plant or whatever that you want to use to as natural coagulant. Sometimes people use coffee bean for natural coagulants, but it is not advisable because coffee bean is expensive. It's expensive and it's food. Okay, so you need to show the how they prepare these natural coagulants for the water treatment system, and also I want you to calculate the amount needed for the quantity of water that is needed to be treated in your water treatment plant. And also I want you to talk about the saving that you will be able to get when you use these natural coagulants instead of the chemical coagulants. Of course, the health effects is something that you need to also discuss. Okay. Okay, so that you will have more things to coagulation and flocculation process in your project. Okay. Okay, so just now we are talking about the factors that affect. Hello. Umi tengah ngajar lah. Okay, the factors, two main factors that affect the coagulation process are the coagulant dosage and pH of the water. So the optimum dosage and optimum pH are determined by laboratory tests called the jar test. So the jar test consists of 6 beakers filled with the water to be treated, and then each is mixed and flocculated uniformly. First, you have to keep constant coagulant and you vary the pH. Then you hold pH constant and you vary the coagulant dosage. So in the end, what you will get is something like this. So you will draw the graph, turbidity remaining versus the pH and turbidity versus alum dosage. So you can find the optimum pH to be used and also the optimum dosage of your coagulant. So because these are two important parameters in the coagulation and flocculation process. Okay. If you have any questions, just stop me. Okay. So design of coagulation tank. Coagulation, for the coagulation tank, we illustrated in the previous slide. Coagulation requires the addition of a chemical called coagulant, and the coagulant should be very well mixed. Should be very well mixed with water to produce homogeneous mixture of the influent water and the coagulant to achieve the best coagulation efficiency. So it must be very well mixed. So this mixing is achieved in a tank we call rapid mixer. Sometimes it is a square tank and sometimes it is a circular cross section, because this is to achieve the best mixing efficiency. Whether you use a square tank or you use a circular cross section tank. So the most common mixers used in the coagulation tank are mechanical mixers. We can have turbine, propeller, and pedal mixers. So because we need the reaction need to be very rapid. So the detention time for flash mixers or rapid mixer is measured in seconds. So whereas for flocculation basin is generally between 5 and 30 minutes. Okay, so coagulation takes only a few seconds, but a flocculation, because you want to have a very the mixing is very slow, so you can have from 5 to 30 minutes of detention time. Okay. Okay, this is the photo on the types of mechanical rapid mixer. Can be propeller, this turbine, or pitch blade turbine. Okay. Okay. Okay, for the mixing, to ensure maximum contact between the reagent and also the suspended particles, coagulants, or sometimes you add the coagulant aids, must be rapidly dispersed or mixed throughout the water. So because otherwise the coagulant will react with water and dissipate some of its coagulating power. So that's why you have to make sure that it is rapidly dispersed. Okay, because otherwise it will the coagulant will react with water and dissipate some of its coagulating power. So meaning that you will need more coagulants. So it will not be economical. So okay. Okay. For you to ensure complete mixings and optimum plug flow reactor operation. So proper detention time in the basin is required. So you can calculate detention time based on this formula. So for complete mixing, this is the detention time. Of course, T over V over Q, but you can, this is also the influent and effluent. So you can, let's say you have the influent concentration, you will be able to determine the detention time is your target is at what concentration of turbidity. So T is the for plug flow system, this is the formula. T, the detention time of the basin, V, the volume of basin, Q, the flow rate, K, the rate constant, influent reactant concentrations, effluent reactant concentrations, L is the length of rectangular basin, and V is the horizontal velocity of flow in meter per second or feet per second. Okay. Okay. How do you size the coagulations of a rapid mixer tank? So this is the, just now that the detention time in the rapid mixer is in the range of 20 to 60 seconds. So actually the short time is enough to achieve complete mixing of the coagulant and to complete the coagulation process. The water depth is usually taken as 1.5 times the width of the tank if it is square, or the diameter 1.5 times the diameter if it is a circular tank. Meaning that the depth of a circular tank, the water depth is 1.5 times the diameter. Okay, so this is the formula for tank volume. V equal to Q, the design flow, multiplied by the detention time in the tank. And also another important parameter for the design of the rapid mixer tank is on the power requirement. How much power you need to provide for the rapid mixing. P equal to mu V G squared. So P is the power transmitted to the water by the mixer, normal meter per second, which is in watt, the tank volume, the velocity gradient per second, and dynamic viscosity of water, normal second per square meter. So this is the power requirement. Okay, so what is the typical design value of the G for coagulation? G is the velocity gradient. What is velocity gradient? It is actually the relative velocity. Okay, it is actually defined as the relative velocity between two colloidal particles in water divided by the distance between them. For example, if you have two particles that are 1 centimeter apart and the relative velocity between them is 10 meter per second, Then the relative gradient, then the gradient is 10 meter per second per 0.01 meter, the 1 centimeter, equal to 1000 meter per second divided by meter, or the unit is per second, per second or this unit. So the detention time or second, if you have detention time of 20, the velocity gradient that is needed, usually it will give you 1000. If the detention time is 30 seconds, the velocity gradient is 900. And if the detention time is 40, 790, and 50 or more, it can be, the velocity gradient can be 700. Okay. Okay, then the flocculation. After coagulation, it goes through the flocculation process. Flocculation follows coagulation in conventional water treatment process. But this is, we are talking about the conventional treatment process. But if you can justify why you, after coagulation, you put something else, and then after that you put the flocculation, you can also do that. Okay, flocculation is a physical process of slowly moving the coagulated water to increase the probability of particle collisions. So through experience, I will not stop at 1 o'clock because I think I can finish the class before 2 hours for this coagulation flocculation process, because it's quite simple. Okay, so please bear with me. Okay, it is a physical process, slowly mixing the coagulated water to increase the probability of particle collision. So through experience, we see that the effective mixing reduces the required amount of chemicals and greatly improve the sedimentation process. And finally, if we can improve the sedimentation process, we can also have longer filter runs and higher quality finished water. So the simple physical process like this is very important, because we will improve the efficiency of our system, but we don't add only the capital cost, like the flocculation process. Okay, so the goal of this flocculation process is to form a uniform feather-like material, which is very dense, tenacious floc that entraps the fine, suspended, and colloidal particles. Okay, so you can also add polymers. So these polymers are often added to increase the speed of floc formation and the strength and weight of the floc. Sometimes we also add polymers during this flocculation process, because we want to increase the speed of floc formation and the strength and weight of the floc. If you increase the weight, then it is more, so it will result in a better sedimentation of the floc. So the then the configuration of the flocculation tank. You can see this here. Configuration of flocculation tank. So actually the most common types of flocculator are pedal flocculator, this one, and walking beam. So this is the pedal flocculator and walking beam. You can see here, this is pedal. It can be vertical shaft pedal flocculator like this, vertical, or you can have horizontal shaft pedal flocculator like this, slowly moving. This flocculator will slow the pedal will slowly move. This one vertical, up and down, and this one, this horizontally move. And also you can have the this one horizontal shaft pedal flocculator, the axial flow pattern. This one horizontal, ni axial flow pattern, and this one, this axial flow pattern. Not the walking beam yet. I'll show you. This is the walking beam. Walking beam flocculator. I think if you go to any water treatment plant, you can see that this flocculator is walking from it is from here to here. It's walking beam. Okay, here you can see that it walks from here to here, and that's why we call this walking beam flocculator. Okay, and we also have another type. This one. Solid contact flocculator clarifier. Just now I told you that flocculation can also be combined with sedimentation tank. So in your design of water treatment plant, you have to decide, and you have to decide and give reason why you use this type of flocculator. Maybe if you want, you think that the cost of the efficiency of the system is better by combining the solid contract flocculator with clarifier, so that you don't have any sedimentation tank in your unit operation, meaning that you save one unit operation. The capital cost will be much different. Okay, and this is the layout. Layout of a water treatment plant. If you have the coagulation process, rapid mix coagulation tank here, and then you have the vertical shaft pedal flocculation tank here. So the water from here to here, and then it goes to the sedimentation tank. Okay. Okay, when you want to design a flocculation tank, so the first important design parameter is the tank volume. Of course, it's easy. V equal to the design flow multiplied by the detention time. So as I mentioned just now, the detention time in the flocculation tank is much higher than that in the rapid mixer of coagulation tank. Okay, so it is in the range of 20 to 60 minutes. So the power requirement, is using the same formula. So, but of course, the G value will be different. The G value will be different because, of course, because you have this flocculation tank is a very slow moving equipment. Okay. Okay, pedal flocculator calculation. So the gentle mixing required by the flocculation, usually you accomplish by a variety of devices. So the most common one is the basin that you equip with mechanically driven pedal. So this is that's why we have this example, the formula for calculation of power required by a pedal flocculator. So pedal flocculators usually have individual compartments for each set of pedals. So the useful power input imparted by a pedal to the water depends on the drag force and the relative velocity with respect to the pedal. So the value of G times T, the velocity gradient times the time of the detention time, is an important parameter factor in the flocculator, because it has a range of what is the range? 10 to the 4, 10 to the power of 4 to 10 to the power of 5. Yeah? And the typical value of G is 15 to 16 per second. Yeah? So this is the common value. So when you design a water treatment plant and you want to use pedal flocculator, so you need to show the calculation, what is the G that you use and what is the power requirement of your system. So the power is also expressed in terms of the pedal mixer properties as the following. So this is the power, this is the drag coefficient, function of pedal blades dimension. You can get all the value here, maybe from handbook, or you can always get from I think from the if you Google the drag coefficient, the area of the pedal blades, the water density value, velocity of the pedal relative to the water value. If you want to calculate very detail on the power for your pedal mixer. And if more than one blade is used on the pedal, the power is expressed as P equal to this formula. Oh, so, okay. And you divide by 2. Okay. Okay, and values of the drag coefficient for pedal wheel flocculator. Length to width ratio L over W. If 5, the CD is 1.2. If 20, 1.5. This is ultimate value. You can have 1.9. So the blade's velocity is related to the rotational speed of the pedals by the following relation. So this is the velocity pi d lambda. So this is the if you want to calculate very detailed on the pedal that you use for your flocculation basin. Okay, actually I give you all the theories, but after this and then at the end I show you the calculation examples for coagulation process. Because if we just give you theory and without showing you how this calculation for the design of 2 units, the coagulation and flocculation, maybe it's a bit confusing. So I show you first calculation examples of coagulation process. So question 1 about the volume of your coagulation tank and the power requirement. So let's say if you are asked question like this, and because by having this question also, you will be able to understand more when you want to design your coagulation and flocculation process. So a rapid mixer is to be used for coagulation of surface water with high turbidity. If the flow is 720 cubic meter per hour, find the volume and dimension of the tank and power requirements. Okay, so you know that these are 2 important design parameters. So of course the solution is very easy, where you can find the volume based on the flow and also the detention time. You assume because you know what is the range. So when you design, of course you do not know what is the most accurate values, but you must assume the detention time from what? Maybe 5 to 60 seconds, because for coagulation process, it must be very fast. So you can assume the detention time is 20 seconds, and what is the gradient velocity that you use. And this is the value that you can get from any handbook for water. So from this value, you will be able to calculate the volume of the tank that you want to use. Okay, so you have to also assume whether you use a square or a circular tank. So of course, when you assume it must be something that is must be correct assumption. You cannot assume you use a tank which is rectangular because the mixing will not be efficient. So you need to use whether it's a square tank or circular tank. So this is what the volume is, W times 1.5 W. Why? Because it's already I've already told you just now that the depth is 1.5 times to the width of the tank. So finally, you will get the dimension for your tank. And then you can also calculate the power required by the for your coagulation process. Question 2 is also example to calculate the volume of coagulation tank. A flash mix chamber is 4 feet squared with water to a depth of 3 feet. So it's given also already. So what is the volume of water in the chamber? So you have to be familiar with all the calculation, with all the design, whatever you need that you use. Okay. And number 3 is about detention time. Assuming the flow is steady and continuous, a flash mix chamber is 6 feet long, 4 feet wide, with water to a depth of 3 feet. If the flow to the flash mix chamber is 6 million gallons per day, MGD, MGD is million gallon per day. So meaning that even if you come across this MGD unit, you need to automatically know that this is million gallon per day. What is the chamber detention time in seconds? So of course, unit conversion is very important. Sometimes the calculation is easy, but you make mistake in the conversion. That's why in the filtration exercise that I give you for last week lesson, I just want you to copy and make sure that you input all the unit during the calculation, so that I know that you are very expert in converting units, because this is very important in calculation. Okay, coagulant feeding. Okay, in adding or dosing chemicals to the water flow, a measured amount of chemical is called for, meaning that a measured amount of it is very, very important for the dosing, because not only that you want to save the chemicals, but you don't want also to get when the chemicals become at certain quantity and pH, you don't want to chemicals to be soluble. So that's why the precipitate must be formed when you use these coagulants. So the amount of chemical required depends on such factors such as the type of chemical used, the reason for dosing, and the flow rate being treated. So if you use dry jar test indicate that one of the problem to show you, jar test indicate that the best LM dose for a water sample is 8 milligram per liter, meaning that whatever quantity that you decide to use for your coagulant, you must start with jar test. Jar test will determine what is the amount of alum needed. If the flow is to be treated, is 2 million gallon per day, what should the pound per day setting be on the dry alum feeder? So meaning that this one is very easy, just to determine pound per day, meaning that the chemical which is in milligram per liter must be multiplied by the flow, and this one here is given million gallon per day, which is 2 million gallon per day, 2.1 million gallon per day, and you have to multiply by unit conversion until you get this, because the chemical the setting is in pound per day. So you must be very expert in converting the units, depending on the chemical feeder setting that you have for your coagulation tank. Sometimes it is also used liquid form. So the jar test indicate that the best alum dose for a water sample is 7 milligram per liter. So you are also given the amount to be treated in million gallon per day. So you have to determine the GPD setting for the alum solution feeder if the liquid alum contains 5.36 pound of alum per gallon of solution. Okay, so this is the solution that you have in hand. So how do you want to make sure that you will be able to feed your coagulation tank the exact amount? So first you have to calculate the pound per day of dry alum required using the milligram per liter to pound per day equation, and this is required, and then you have to calculate based on the solution that you want, the concentration of solution that you want. The solution here is, it says here that you need 5.36 pound of alum per gallon of solution. So finally, what is the gallon per day that you need for the alum solution for your this amount of flow? Okay. And this one, let's say if the chemical solution feeder is set at milliliter per minute. So the problem is not difficult, but it's just for you to ensure that you know how to convert the unit from one maybe SI unit, English unit to the other. Okay. Determining percent of solution. The strength of solution is measure of amount of chemical solute dissolved in the solution. We use the following equation to determine percent strength of solution. Okay, so let's say you get the you prefer to feed your coagulation tank using solution because I think it's easier and it is more accurate. It is easier for you to use the flash mixer if you have solution. So calculation on the percent strength of solution is very important because you want to have an accurate calculation. So percent strength is the chemical, the weight of chemical divided by the weight of water and the chemical. Okay, so this is what you mean by percent strength of solution. So now calculate percent strength. What is the percent strength that you have if you have let's say you have 0.625 pound chemical. So you have the water 15 gallon. You have to multiply by the unit here, and then you have to add the amount of chemical that you have. Then from here you get the percent strength of your coagulant. And determining percent strength of liquid solution. This is also calculation on determining the percent strength. Let's say if you have liquid polymer, so the liquid polymer percent strength divide by 100 because you only have the polymer. Okay, so for example, a problem on a 12% liquid polymer is to be used in making up a polymer solution. How many pounds of liquid polymer should be mixed with water to produce 120 pounds of a 0.5% polymer? Okay, so this is what you want. Okay, so this is what you want, this is what you have. Finally, you want to find the X, meaning the amount of polymer that you need to put in a 120 pound of water. So this is the example of calculation. And if you have mixed solution, let's say you use coagulant and you have also alum and also you have the lime, you can also calculate the strength based on the strength of mix. The first solution and the second solution here. So when you come across this and you want to calculate, you can just follow each step easily, and it is provided here so that you can understand. Okay, calculation examples for flocculation process. So for the coagulation process, the important parameter is the size of the tank, the power needed, and the detention time, and also the feeder setting, and also the amount of chemicals that you want to use for your flash mixer tank. Okay, for the calculation examples for flocculation process, this is question 1. This is when you combine the coagulation and flocculation process. First is the detention time. Alum dosage is 40 milligram per liter. K, which is the rate constant, is 90 per day based on lab test. So compute the detention time for complete mixing and plug flow reactor for 90% reduction. So as I mentioned earlier, that you can also have the coagulation and flocculation tank together. So the detention time will be based on the flocculation time, because flocculation is where you have a very comparatively long detention time compared to coagulation. So you want to have 90% reduction of your turbidity. So you need to calculate what is your CE. CE meaning concentration of the effluent reactant concentration, 90% reduction. So this is the CE, this is the CI, influent reactant concentration. And okay, so you calculate the T, the detention time. For complete mixing, you use equation that I gave you earlier, and you can also calculate T for plug flow. So you can compare. If you use a plug flow system, the detention time needed is only 36.8 minutes, which is almost the amount of time, the common detention time allocated for a flocculation tank. But if you use mixing, complete mixing, maybe in a square or in a circular tank, the detention time is 144 minutes for you to have 40%, 90% reduction. So in your design, maybe you can say that you use a plug flow flocculation tank. Okay, and question 2, this is also example how you calculate the GT value, the basin dimensions, and also the power to be imparted to the water in each compartment. Okay, so I think you just carefully read through the question here, and then you see all the calculation, detailed calculation here. Okay, so this is for you to determine the GT value, basin dimension, power to be imparted to the water in each compartment. So for the flocculation process, the important design parameter that you need to know and you need to put in your design of your water treatment plant. First is the detention time. Then the basin dimensions and the power imparted to the water in each compartment. So the GT value will also be together with the power to be imparted to the water in each compartment. If you use 3 different compartments like what we have here, cross flow, horizontal shaft. Okay, so you have to have carefully think and determine based on the requirement of what you needed in your effluent removal. Okay, So this is another examples of determining the volume of the flocculation basin. Okay, so I finished everything on the coagulation flocculation. It is very simple, so I hope that you can understand. You can ask question. Do you have any question, students? Do you have any question now?
Prof.
No, okay, good.
Prof, nak tanya.
Yeah.
Yang for next week presentation tu, yang water quality estimation tu nak cakap pasal apa?
Quality estimation. The water quality analysis.
Yang satu lagi tu.
Quantity.
Quantity. Oh, sorry, quantity.
Water quantity meaning that you have decided on the location of your water treatment plant. So this one is something that you assume, because after you get the location, you see that there are maybe the water treatment plant is to supply water to which community. Okay, so you can show me in the map where is the community that you want to serve, and you can decide if it is not it is not stated in the reference journals or whatever. You can always assume how many population that you want to supply using your water treatment plant. Okay, because by having this quantity, then only you can design your treatment plant. Okay, and also all the units, they need quantity and quality of your source water. So it's like your own creation of the community that you want to use, that you want to supply the treated water. Okay, so it's easier. So because you see in my first slide, I think I've already taught you how to calculate the quantity of the water supply needed, right? And also those of you who have taken water supply in KH3113, you also can estimate the amount of water needed for that community. Let's say if you want to build your water treatment plant for that community, then you can tell me from which the value that you get is based on what estimation of the community that need to be served by your water treatment plant. Okay, is it okay?
Okay, Prof.
Okay. So every time, every topic, I will give you the quiz or homework. Homework, because I want to make sure that each unit that you study, you know actually what the important issues or things that you need to absorb from the materials. Okay, last week I gave you that just to copy the examples that you have in the filtration. For this coagulation flocculation, most of the time I want to give you quiz. So on you read the material for today after the lecture and you are still fresh. And then on Tuesday you will have quiz or homework if I have finished the part that I need to describe in class. So for tomorrow is a public holiday, but I want to give you quiz on this topic, on this coagulation flocculation process. So what time do you want me to give you the quiz? It's simple. By just reading through the slides on this coagulation flocculation process, you will be able to answer the quiz very well. So, and this quiz, the marks for this quiz will be counted in your final marks. Okay, when do you want me to have the quiz? You want tomorrow or next week? Next week when you have this presentation, maybe any times not during the presentation time. Because I have to set the time. When is the, can I give you quiz tomorrow? Huh? Is it okay if I give you the quiz tomorrow at 9? Or you want at a later time? Only 1 hour, not only 1 hour. I think half an hour you can finish. When is the suitable time for you I try to accommodate your convenience for having this quiz? When? Somebody just tell me, and then the rest need to follow because they are quiet. Okay, what time you want? Only on the materials for this slide, coagulation, flocculation process. Because I'm afraid that I will not be able to ask all questions in your final exam. So I just want to make sure that I ask questions for all the parts that you have in your course. Because I don't give you mid-sem exam. So this quiz is also important. When is the quiz time that you want? Is it tomorrow, 9 o'clock?
Tomorrow. Okay,
tomorrow, 9 o'clock. 9 o'clock.
10 boleh, Prof.
Okay, 10. Okay, 10. So the rest need to follow because you are all quiet. So just now who's telling me at 10? Dirham, eh?
Amirul.
Huh? Amirul. Amirul. So you need to follow the time chosen by Amirul. Okay, so tomorrow at 10, you will have a quiz on this coagulation flocculation process. Just read through one time and also the examples on the calculation. Okay. Okay, see you again next week. Okay, so tomorrow at 10, I will I will on this UKM folio, the quiz in the UKM folio, the time. Okay, see you all. Okay, you can always ask me about your small presentation. You can always ask me in the groups. Okay, see you. Thank you.
Thank you.
Welcome. Thank you, Prof.
Thank you, Doctor.
Yeah, welcome.